Hello, welcome back to the channel. So let's continue our previous video and do one more question on the volume calculation of solids using definite integrals. So before solving this question, if you have not watched my previous video, I would highly suggest you to first watch that video in order to get the full context of what we will be doing in this video, because this would be a fairly tricky problem to solve compared to the last problem that we solved in the last video. So that is why I would highly suggest you to first watch that video, which you can also find on the I button above. So now we have to calculate the volume of the solid obtained by rotating the finite plane region bounded by two curves in this case. Remember, in the last question it was only one curve, but this time we have to first calculate the region bounded between both of these curves, and then after identifying the region bounded between both of these curves, we have to rotate the finite plane region about the line y equals -1 in this case. You know, y equals -1 would be a horizontal line which passes through y equals -1, right? So again, this question may seem intimidating at first, but if you know a general idea about how to solve these type of questions, if you have enough practice on how to solve these type of questions, you will be able to easily solve these type of problems, because we know in these cases that both of these are indeed parabolas, right? This is an inverted parabola and this is also an inverted parabola as well, right? So we know most things about our curves. The basic idea is to again just identify our aerial strip and calculate the area of our aerial strip based on the familiar mathematical calculations that we already know. And that is what we experienced in our last video as well, when we took the area of a circular strip. So in this case, since you have two curves, you'll first have to again identify the intersection points. The same thing that we used to do for our horizontal strips or vertical strips calculation. We first used to identify the intersection points, and then based on the intersection points we'll identify the region bounded between both of these curves, and then afterwards we'll do the rotation in this case again. So if you have to calculate the intersection points in this case, you'll again equate the y or the x values. So in this case, since it's easier to equate the y values, we'll take the y values over here. So we'll equate 1 minus x square with 4 minus 4x square. If I shift x square to the other side, 1 to the other side, 4x square minus x square, this would be 4 minus 1, right? This is 3x square equals 3, x square equals 1, x equals plus minus 1. So now we have identified the intersection points, which are x equals 1 and x equals -1 in this case. And now, based on these two curves, let's sketch the graph of both of these functions and also shade the respective region bounded between both of these curves around the intersection points. So now we'll sketch the graph of both of these functions. We know that both of these are parabolas. So this is our y equals 1 minus x square, and this would be our y equals 4 minus 4x square in this case, right? And again, the region between these curves is basically this region, right? Okay, so now the first task is done, where we had to identify the region bounded between both of these curves, and that was simple, right? And now the next part is to rotate this region about the line y equals -1 in this case. So now let's do some visualization and rotate this area about y equals -1 in this case. And you'll notice that when you'll rotate this area, you'll have something like this, and if you'll extend this one and extend this one as well, you'll have something like this, right? This might not be the perfect visualization, but you can clearly see in this case that it would be identical with this area, right? The region that you would have below this line would be identical to the upward area, right? But just flipped around. So now when we'll take a vertical strip and build an arbitrary aerial strip around that, you'll notice that you you'll notice that when you're rotating this arbitrary strip, like a strip around the line y equals -1, you are basically building two circles over here, right? So now you're basically building, while rotating, this bigger circle over here, and also This circle is formed when you'll rotate your upper y value around the line y equals minus 1, right? But again, when you'll rotate this one around the line y equals minus 1, you'll see that you're making another vertical strip over here, which is this one, right? So there are basically two circular strips over here, and if you'll visualize this in 3D, so basically what you're doing is you have one circle over here, like the blue circle, which is the smaller one, and the green circle over here is the larger one in this case, right? So now you have two concentric circular strips, one with this radius and the other one with the larger radius, right? The one including this one. However, since you know that you're only concerned with this area over here and similarly this area over here, so you'll see that that is basically subtracting the area of the larger circular strip with the area of the smaller circular strip over here. I know it's harder to visualize, but if you'll try to rotate this vertical strip around y equals minus 1, you'll see that you are basically forming two circular strips, one with a larger radius and the other one with a smaller radius. And you'll see in this case that in order to calculate the area of your region, your enclosed region, you will have to basically subtract the area of the larger strip with the area of the smaller circular strip in this case. So again in this case, when you'll calculate the radius of your circular strips in this case, you'll see that if we have to calculate the radius of the smaller circular strip, that would basically be subtracting our upper y value, which is based on this function, with our lower y value, which is based on this function over here, right? So if we have to calculate the inner radius over here, let's erase this, and if we have to calculate the inner radius over here, that would be basically subtracting our lower y value from the upper y value. So the upper y value is based on y equals 1 minus x square. So 1 minus x square minus of the lower y value is y equals minus 1 in this case. So minus of minus 1 in this case, right? So the inner radius in this case would be 1 minus x square plus 1, which would be 2 minus x square in this case. So you have identified your inner radius. Now it is the time to identify our outer radius in this case. So again the outer radius would be subtracting the lower y value from the upper y value. So the upper y value is based on this function and the lower y value is again based on y equals minus 1. So the outer radius in this case would be, your outer radius is 4 minus 4x square, your upper y value, 4 minus 4x square minus of minus 1, right? Because minus 1 is your lower y value in this case. So the outer radius is 4 minus 4x square plus 1, which would be, the outer radius would be 5 minus 4x square in this case, right? And now again, since in this case the required area of our arbitrary aerial strip is basically subtracting the smaller area, the smaller circular area from the larger circular area. So now we'll calculate the areas of our inner and outer aerial strips. So now the area of our inner circular strip would be basically pi times our inner square, and similarly if you have to calculate the area of your outer circular strip, it would be pi times our outer square. Again we have calculated all this, so this would be, A inner would be pi times 2 minus x square whole square, and our A outer would be pi times 5 minus 4x square whole square, right? And now since we again know that the required area of our aerial strip is basically calculated by subtracting both of these outer and inner areas. So the final A in this case would be simply A would be A outer minus A inner, right? Because that is the required area of our arbitrary aerial strip. So you'll subtract this out. It would be 5 times 5 minus 4x square whole square minus 5 times 2 minus x square square. And now you know that in order to calculate the volume, if you want to calculate the volume, you basically take a dx around the endpoints given, and since we already calculated the endpoints in this case, which were x equals minus 1 to x equals 1 in this case, so you know that your final volume would be integral x equals minus 1 to x equals 1. Your a is basically this expression over here. So your a is pi times 5 minus 4x square minus 5 times 2 minus x square multiplied with a dx in this case, right? So multiplied with a dx in this case. And when you'll solve this definite integral, you will be able to calculate the area bounded by rotating the finite plane region between the curves y equals 1 minus x square and y equals 4 minus 4x square about the line y equals minus 1. I know this was a tricky question to solve. The hard part is always to identify the area of your arbitrary vertical strip, the required area of your arbitrary vertical strip, and then integrating over the endpoints in this case. So again, a quick overview on this question, on these type of questions. When you have to solve these type of questions, you first, when you have two or more curves, you first identify the intersection points. That is what we did first. Then you sketch the graph of both of these functions. You identify the region bounded between both of these curves, and then you basically rotate the area around your given line and visualize the volume of the region being formed. And after you have visualized, you'll take an arbitrary aerial strip, and based on your arbitrary aerial strip, you'll calculate the required area of your arbitrary aerial strip, which in this case was basically subtracting the area of our outer circular strip with the area of our inner circular strip in this case. Again, I would suggest you to spend some time on this question and clearly visualize why we took the difference of the areas in order to calculate the specified area, the required area of our arbitrary aerial strip. Because I totally agree that it was not easier to identify the required area of our arbitrary circular strip in this case. So that's it for this video. Feel free to comment down in the comment section below if you have any doubts regarding this question or regarding the concept in general as well. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.